In this video, we're going to talk about how to implement embedding in PyTorch. So, let's see the big picture first. Embedding converts words into vectors like list of numbers. Example, keying is convert the vectors into a list of numbers 0.25, negative 0.71, 0.88. These vectors are not random after training. They become geometric representations of meaning. Words with similar meanings end up close together in vector space. Example, queen, prince, monarch will cluster near each other, while apple, banana, mango form another cluster. That is the core idea of semantic embeddings. So, what is static embeddings using the globe? Uh, like, globe means the global vectors for word representation. It is called static embeddings model. Why static? Because each word has only one vector. Example, apple always same vector, king always the same vector, bat always has the same vector. No matter where the word appears. How globe learns meanings. Globe learns from nearby words, occurrence statistics, context frequency. Example, if word king often appears near queen, royal, throne, prince, then their vectors become similar. This is exactly the semantic learning concept. The model discovers relationship automatically from huge text corpora. So, Glove dataset. The lesson mentions Glove 6B dataset, trained on Wikipedia plus GigaWord. 6 billion tokens, 400,000 vocabulary words. A token usually means a word or subword processed during training. So, embedding dimensions. So, like for example, if we have the 100 dimensional vectors, meaning the word king has 100 set of numbers, 100 numbers, not just 2 or 3 numbers. Each dimension helps encode semantic information. Important idea here is the dimension are not manually assigned, meaning like dimension 1 royalty, dimension 2 is gender. Instead, the neural network automatically discovers full geometric patterns during training. Concepts becomes distributed across many dimensions together, exactly like what we discussed in the previous videos. So, what is cosine similarity? The lesson in our study compute semantic similarity. So, the main idea is two vectors pointing in similar directions have similar meaning. Like if we calculate the cosine of this theta or the angle cosine, we calculate it as a multiplied by b divided by the absolute value of a multiplied by the absolute value of b. If cosine similarity is close to 1, that means it's very similar. If it is close to 0, that is unrelated, and if it is negative, that's opposite direction. So let's find the similar words. The code takes first the code takes the target vector. Second is compares against all vocabulary vectors, and next is computes cosine similarity and returns to the closest word. Example, if find the king, and it may return queen, monarch, prince, throne, because their vectors are nearby in embedding space. So this is a famous embedding analogy. So the lessons demonstrates the king minus 1 plus woman is equal to queen. Geometrically, king vector minus male concept plus female concept. So the results near queen vector. This is one of the most famous embedding illustrations. The important insight is embeddings learn relationships mathematically, not just similarity. So why this works? Because semantic directions emerge inside vector space. Example, one direction in high dimensional space may roughly encode male to female. Another may encode royalty. So vector arithmetic becomes meaningful. That is why king minus 1 plus woman lands near queen. So what is the limitation of static embeddings? Now comes the biggest weakness of Globe is polysemy, meaning a single word can have multiple meanings. Like for example, a word bat could mean animal, baseball equipment based on the sentence or a sentence that we use. Like but Globe gives only one vector, like but same embedding always. So these sentences a bat flew from Kiev and he swung the baseball bat, produced the same embedding for bat for static. Why static embeddings fail here? Because globe averages all context during training. So animal bat context plus sports bat context becomes merged into one vector. This loses contextual nuance. So here comes the contextual embedding like BERT. This is where BERT becomes powerful. BERT generates embeddings dynamically based on surrounding words. Meaning bat in word in different sentence in cave sentence gets a different vectors from bat in a baseball sentence because surrounding context changes the representation. So let's understand more in depth in the contextual. So let's say we have the sentence 1, a bat flew out from the cave. And Bert understands bat is equal to animal. In sentence 2, he swung the baseball bat. Bert understands it as a bat is a sports equipment. So embeddings becomes context dependent. This is one of the biggest breakthrough in natural language processing. So how Bert produces embeddings, the lessons mentions tokenized sentence, encode tokens, pass into Bert, extract hidden states. The hidden states are contextual embeddings. Like for example, outputs in the Python or PyTorch outputs that last hidden state. This tensor contains embeddings for every token, exactly related to our earlier questions about output 1 that last hidden state 0. Meaning, batch index 0 retrieve all token embeddings for the first sentence. Why BERT is powerful? Because meaning depends on context. Example bank could mean riverbank, money bank, static embedding struggle. BERT adapts dynamically. This is why modern NLP or natural language processing heavily uses transformers. So static versus contextual embeddings. So static or globe advantages is fast, lightweight, memory efficient, good for simple tasks, and disadvantages of it cannot handle ambiguity, one vector per word only. While the contextual or using the BERT advantages is understands context, handles polysemy, deeper language understanding. So its disadvantages is computational expensive, slower, more memory usage. So when to use each? Use static embeddings when simple classification, limited hardware, fast inference needed. Use contextual embeddings when chatbots, summarization, question answering, translation, advanced natural language processing, because meaning depends heavily on context. So let's see the embedding visualization. So the problem, humans cannot visualize 100-dimensional space, so we reduce dimensions to 2-dimensional or 3-dimensional for plotting. We use the PCA, or one method is PCA. So the formula is x subreduce is x multiplied by W conceptually. PCA finds direction with maximum variance, meaning it tries to preserve important information while compressing dimensions. So another method is TSNA. Goal is preserve local neighborhood relationships. So the meaning words close in high dimensional space remain close into the two-dimensional visualization. It produces visual intuitive clusters, but slower computation expensive. Next is semantic clustering. Vehicles clustered together like car, truck, bus, motorcycle. Fruits clustered together like they're clustered like apple, banana, mango, and flowers clustered together rose, tulip. This visually proves embedding capture semantics. So important real-world concepts. So higher dimensions, more dimensions means richer semantic representation, more expressive power, but also more memory, more computation, more training data needed. Trade-off always exists. Embedding initialization. What is this? To approaches random initialization. Start with random vectors. We use the PyTorch or Python the torch to run the train from scratch. Pre-trained embeddings uses pre-trained models like Globe, FastText, BERT, and its advantages is faster training, better performance, useful when data is limited. Next is out of vocabulary problem. What if a new word appears? Example, ChatGPT Ultra 9000. It's not seen during training, so the solution is UNK token. Use specialized known token. Okay, subword models like fast text. They split words into similar pieces. Example: unhappiness and plus happy plus less. This helps generalize to unseen words. So here are the final core insights. So embeddings transform language into geometry. Words become positioned in high dimensional space. Neural network can then mathematically process semantic meaning. So that is the bridge between human language and neural network computation. So this is the overflow of the natural language processing embedding from the text. It's tokenized. It token the IDs. Its embeddings like vectors, present in neural network layers, and produce the predictions.